This is our final presentation for statistical machine learning. We decided to present on our classification question, which is exploring what variables are significant in predicting whether someone will default on a loan or not. Intuitively, the variables we first considered are information about the person taking out the loan, like their income and their credit score. So we ask, is a loaner with a higher credit score or income less likely to default than those with lower credit score or income? We also wanted to consider information about the loan, like the amount or the interest rate. We will be exploring these variables and more and their relationship with someone defaulting on their loan. Our motivation for this question is that we all had an interest in how machine learning methods could be applied to financial data and how it could help businesses make informed decisions. In this case, it can help lenders make decisions about whether to approve someone for a loan based on their likelihood to default. About our data, it was collected from Kaggle, which sourced it from a Coursera challenge. Later on, we will discuss about possible issues with the data and how it could have affected some of our conclusions. Each row contains information about a loaner and the loan that they took out. These are things like age, income, loan amount, credit score, interest rate, education, which is a categorical variable correlated to the loaner's highest level of education, and debt to income ratio. Our response variable is a categorical variable called default, which is yes if someone defaulted and no if they did not. And then we move on to our EDA. On the slide, we included 4 of our most significant visuals. These box plots confirm our initial intuition about the predictors. As you can see, those that did not default had higher median age and higher median income. They also had lower median loan amount and lower median interest rate. We had 5 categorical predictors that we investigated as well, but they did not show much of a relationship with the response visually. And although only these 4 showed to have a relationship, we kept all predictors to investigate further.
To analyze our classification question, we first needed to determine if logistic regression or a linear discriminant analysis was better suited for our data. When performing LDA, we first had to check the multivariate normality assumption, and we used the kurtosis test and the skew test to check for this. The kurtosis test found that the alternative hypothesis, or that the distribution of the predictors is not consistent with a multivariate normal distribution, to be true. However, the skewness test found that the null hypothesis was true. Based on the results from the kurtosis test, we have evidence that the assumption for discriminant analysis may not be met, and therefore we're not able to make reliable interpretations from our LDA. For that reason, we've decided to use logistic regression to explore our classification question. To analyze our question of what predictors are significant for determining loan default, we used a reduced logistic regression model. To analyze the effectiveness of this model, we used the ROC curve and AUC value. Based on the ROC curve and the AUC value of 0.7333, we established that this model was better than random guessing. From this, we determined that age, income, loan amount, and interest rate are significant predictors for loan default. We were not surprised to find that someone with a lower age, lower income, higher loan amount, and higher interest rate are more likely to default on a loan. However, we were surprised that more of the predictors were not significant.
And our next step was to explore how our data performed with classification trees. So with recursive binary splitting, we get a classification tree that uses 7 of our 11 original variables, producing a tree with 14 terminal nodes. This model has a training error rate of 0.123. And this tree shows age as the most influential predictor of whether or not someone will default on their loan. Interest rate and loan amount are also significant predictors, and new predictors emerge depending on the values at each stage of the tree. At a threshold of 0.5, the false negative rate for our recursive binary splitting model is extremely high. In this context, a false negative means that you would wrongly predict that someone would not default on their loan, when in reality, they would default. This could cost a lot of money for the organization distributing the loans, and therefore we feel that the threshold should be lowered. Although the accuracy decreases with a threshold of 0.2, our false negative rate decreases significantly, indicating that this threshold is better in context. Next, we prune the tree created from recursive binary splitting in an attempt to simplify the model. However, this prune model only had 1 terminal node, meaning that none of the predictors are significant enough to impact the response variable. All observations in this model would be predicted by the majority class, which is to not default. Despite the simplicity of this model, we note that this model is actually more accurate than the one created from recursive binary splitting. Although the false negative rate is very high, all observations will be classified as no matter the threshold, so we will not make an adjustment here. And lastly, we computed a model with random forests. However, both graphs show different predictors to be significant, which leads us to believe that this is not a good model of the data, and none of these predictors are very good indicators of loan defaults. And like recursive binary splitting, a threshold of 0.5 produces an extremely high false negative rate, which is problematic for lenders in our context. A threshold of 0.2 causes our false negative rate to decrease significantly, so this threshold, again, is better. Once again, the impact of a false negative would cause more monetary loss for a loan distributor than the false positive rate.
Following our analyses, we wanted to do a final comparison of our methods. In terms of error, the best model was random forest with a 0.5 threshold. This model, however, had an extremely high false negative rate, which we wanted to minimize. The models that best balanced error with the false negative rate were the recursive binary splitting and the random forest with thresholds of 0.2. Logistic regression, recursive binary splitting, and random forest found some similar predictors to be significant, which ended up being age, interest rate, income, and loan amount. This is very different from the pruning, which found none of the 11 variables to be significant. In terms of interpretation, the same three methods answered our question the best because they showed us which of the predictors had more of an impact and allowed us to make conclusions using those. Since no predictors were significant with pruning, we cannot interpret their effects. In the real world, it's important for lenders to know that these variables are the most important factors in predicting whether someone will default on a loan or not. While running these analyses, it was surprising to us that our variables were not as significant as we had initially thought. Even though we started with 11 predictors, the prune tree ended up with one terminal node, classifying none of the predictors as significant. Another thing that we found interesting is that even our best model had a high false negative rate. This means that people are frequently being misclassified as not defaulting when in reality they do. This could lead to a loss of money and resources for the lender. In this situation, a high false negative rate means that perhaps a different set of methods or predictors should have been used to have accurate predictions for this question. Lastly, after struggling with finding significant results, we discussed the possibility of the data we chose being simulated. This could have contributed to the assumptions not being met and some other issues that we had along the way. We would suggest that either the origins of the data be investigated further to see if it's simulated, or proceeding with the same research question on a different data set. Thank you for your time, and we hope you found our presentation insightful.